Hiya 13. We are going to look at simple harmonic motion, the velocity of today. We're going to start with the reference circle and we're then going to do some formulas about it. Here we go. So this is lesson 2 of the board works of simple harmonic motion. This here is the reference circle. You had an object here going up and down. It was pendulum and it did that. All right. When it is at the equilibrium position, its velocity upwards. So it is slowing down there to when it gets to the apex. So if it was to swing like this, apex here, it's actually momentarily stopped and it then starts accelerating backwards towards the equilibrium position, velocity at the maximum of the equilibrium, and then starts slowing down again to the other apex over here. So that was going up and down here. We had a wheel going around like this. Remember, reference circles always go anti-clockwise. And we had a bob on it here. The shadow from this and the shadow from that match each other, which means they relate to each other. Now, this arrow here is the velocity phasor. So it's a rotating radius, and it's called the phasor. Now you already know that the angle here is rotational displacement. If I draw the tangent to the circle here, that will represent the linear velocity of the reference circle. This linear velocity will be a constant because if you remember, the reference circle was going at a constant speed. The vertical line here represents the velocity of simple harmonic motion. So that's the velocity of the object, which is changing because it's going at a maximum here, and it's going 0 here, maximum here, and 0 here. So velocity is 0 at the apex for an instant. That kind of makes sense when you look at what happens to the direction of the phasor. So in this position here, not of the phasor, of the linear velocity. In this position here, it's directed slightly upwards because it's moving slightly upwards. Here, that linear velocity of the reference circle is horizontal, which means it does not have a vertical component to it, which means that vertically it has a velocity of 0. And then when it's down here, it's then got a velocity with a downward component. Here is going to be at its maximum. It's because it's at the equilibrium position. So this line here, if you remember, is the equilibrium. And down here, it will be at the apex again, and its velocity will be 0. So I'll put some notes down there for you. You can pause and have a copy of that. This triangle here, though, we need to look at it in some more detail. So this angle there is the angular displacement of the phasor. This triangle here has the hypotenuse is the linear velocity of the reference circle, and the vertical line there is the same as the velocity of simple harmonic motion of the object. Now, over to our equations. From rotational motion, I'll just turn you around a bit. From rotational motion, you know that to get a linear quantity from a rotational quantity, you need to multiply it by the radius. So here you go. Convert rotational motion to linear, you're going to have to multiply the rotational motion by the radius. A, if you remember, was the amplitude, so that would have been the radius of the reference circle when we were looking at pure rotational motion. So VL, which is our linear velocity on that triangle there, is equal to A, which is the amplitude, times the rotational velocity. If you look on the small triangle now, cos theta equals the adjacent over the hypotenuse. which cos theta is the velocity of simple harmonic motion, that's the vertical bit, divided by AW, which is the hypotenuse. So VL has been replaced by that. All right, nothing difficult so far. You can rearrange it to the velocity of simple harmonic motion is AW cos theta. From the last lesson, so the first board work lesson, we talked about theta being equal to WT. It means you can substitute WT in for theta there. This formula here, that one, is the one which is on your formula sheet. It is really useful to know where the formulas come from. It is really useful to know that this linear velocity here of the reference circle also represents the maximum velocity. So if the thing was here, it means that the linear velocity will be straight upwards, won't it? There won't be any velocity components that way or that way, so the linear velocity would be straight up there, which means that the velocity maximum equals AW. I shall put it here for you. Velocity maximum equals AW. It is important to know where that came from, and it's because if the object is here, displacement is 0 from the equilibrium position. So the formulas that we are doing at the moment work when we are measuring the angle from the equilibrium position. So our timing has started from the equilibrium position. Once we've finished all this bit, when we've done acceleration and we've related the phases to each other, we will then look at the other set of formulas where we can start measuring the timing from the apex, which is obviously 90 degrees out, or a half pi in radians. All right, so that's the end of this lesson. Next one's on acceleration, and we'll be getting that soon. Thanks.